Welcome back to the first course in general physics. And in this lecture, we will be talking about the second part of the subject concerned with the discussion of the motion of a system of particles. In the last lecture, we have defined this special point for a system of particles and a rigid body, which is called the center of mass of the system or of the body. And in this lecture, we will continue with the same topic and pick up a simple example in order to demonstrate how can we utilize the symmetry considerations, the geometrical symmetries of objects to simplify the problem of determining the center of mass of an otherwise complicated looking object. Then we will use the definition of the center of mass location in order to arrive at a formula which gives the form of Newton's second law as applied to a system of particles. After that, we will define a new quantity in physics, in dynamics specifically, and this quantity is called the linear momentum. We will define the linear momentum for a particle, and then we will state the general form of Newton's second law in terms of this quantity, the rate of change of this quantity, in fact. And then we will derive a formula for the linear momentum of a system of particles. After that, we will couple Newton's second law in its most general form with a basic principle which we call the conservation of linear momentum for a system of particles. And now we consider the concept of symmetry in determining the center of mass for a system of particles. As we have mentioned in the last lecture, sometimes the system is simple, like consisting of two particles or three particles along a straight line or along two coordinates, and the problem is particularly simple to calculate its center of mass, the center of mass of the system. However, sometimes we encounter a problem which involves an object that looks complicated. It looks as if it were composed of different parts put together, and the total shape is complicated, and it is very difficult to evaluate the integral in order to calculate the center of mass for such an object. In this case, we look for other methods to simplify our problem. For one thing, we look for symmetries, geometrical symmetries of the object. If the object has a uniform density, then the problem is greatly simplified, since in this case the geometrical center of the object is the same as the center of mass of the object if the density of the object is uniform. So in this case, we look for the geometrical system, its center of the object, and that would be the location of the center of mass of that object. That simplifies the problem, as we said, greatly. However, sometimes we encounter an object which is more complicated than that. Suppose that we have, for example, a building, and on top of that building is a dome. We can divide this building into two parts. One part is the squarish or the rectangular shape of the building, and consider that this the center of mass for that part is the geometrical center, for example, assuming that the distribution of matter is symmetrical in all parts of the building and the densities are uniform. And the second part of the building would be the dome. So if we find the location of the center of mass for the building and the center of mass for the dome, then we have reduced the problem to a problem which consists, to a system which consists of only two particles. One particle representing the squarish building or the rectangular shaped building, and the other particle representing the dome at the center of mass of the dome. And then we have reduced our problem in such a manner to the problem which consists only of two particles located at two positions which are defined, which are the center of mass for the squarish building and the center of mass of the dome. So in this manner, we are able to simplify the problem of evaluating the center of mass by looking for symmetries. And here we take an example of a shape that we have just selected randomly in order to just illustrate the usage of this of the symmetry considerations in determining the center of mass for an object that looks somehow complicated and difficult to integrate over. Let's assume that we have an object that looks like this, which is partly a sphere of radius r and mass m1, and a long rod of length L of mass m2 attached to the surface of the sphere. So if we have this type of shape, this type of object, if we recall the definition for the center of mass in terms of an integral over the coordinates of the body, it would seem difficult to evaluate such an integral given the shape of these objects. However, we can use symmetry considerations and divide, in that sense, the object into two parts. We can divide the object into a sphere, as if it were alone, and a rod, as if it were alone. So it's like we have two objects instead of one, two bodies instead of one. Now, the rod is a uniform body and we assume it has a uniform density, the whole body has a uniform density, so it would be easy to determine the center of mass for the rod. Also, the sphere being a uniform body, spherical shape, it's also easy to determine the center of mass for the sphere. The center of mass of the sphere, since it has a uniform density, is at its geometrical center, which is the center of the sphere itself. We call that point, which is the center of the sphere, the origin O. We just select that point for convenience to be our origin. So we have the first object is like a point with mass m1, which is the mass of the sphere, located at x1 at the position x1 equals 0 and y1 is equal to 0 and z1 is equal to 0. That is the location of the center of mass of the sphere of radius m1. Second, we move to the rod of length L, and from the symmetry we realize that the center of mass of the rod is at its midpoint, at its center. The midpoint is a distance L/2 from an end of the rod. Thus, relative to our reference point, which is the origin, the center of mass of the rod, which is x2, is located at a position x2 equals r, which is the radius of the sphere, plus L/2, because we are measuring the position relative to the origin. So now, instead of having this complicated shape of body, we have reduced our problem into a problem which consists of two point-like particles, one having mass m1 at x1 equals 0, and the other one is having a mass m2 at x2 equals r plus L/2. So we have reduced the problem into these two particles, and those two particles are on a straight line, located on a straight line, and we call that straight line the x-axis. So we have two particles on the x-axis with known masses and with known locations or positions. So the problem is easily solved, and the center of mass is evaluated by using the previous definition for the center of mass of two particles. So we have x center of mass is equal to the first mass times its location, its position, which is m1 times 0, plus the second mass times its position along the x-axis, which is m2 times r plus L/2, all divided by the total mass of the system, which is m1 plus m2. And if we reduce this formula, simplify it, this will look like m2 over capital M, which is the total mass of the system, multiplied by r plus L/2. So that is the position of the center of mass of this body that we have considered. We have demonstrated that we have solved the problem very accurately and in a simple manner, very simple manner, just by using the symmetry considerations. For just consistency, check the units on the left side and on the right side of the equation. On the left side, we have x center of mass, which should have units of length or meter in the international system. And on the right-hand side, we have the mass over mass doesn't have any length, any units, and the remaining quantity in parentheses, which is R plus L over 2, also has units of length or meter. The unit is meter in the international system. So the consistency of the units is there in this result. This is a demonstration, again, of how we can use the symmetry considerations in simplifying our problem and solving a complicated shape of objects, solving for its center of mass and finding it by this simple method. Now we arrive at a point where we are ready to state Newton's second law for a system of particles. So far, we have stated and used Newton's second law when applied to a particle or to an object that moves like a particle. And now we define the second law of Newton for a system of particles. Imagine that you drive a cue ball into a second billiard ball while playing pool. If the second ball is stationary, then you would expect that after the cue ball hits the second ball, the two balls will continue moving in a sort of forward motion. If the collision is head-on, then the two balls will continue moving forward, or in some sort of forward motion. But the net motion will be forward. That is what we expect, and that is what our experience tells us. You will never anticipate that hitting a ball, a billiard ball with the cue ball, you will never anticipate that these two balls will come back to you, or they will turn left, or they will turn right. You will never expect that. And if this happens, you will think directly that something is wrong. Something is wrong because it's not consistent with nature and natural phenomena. And this is correct. Our experience tells us that in such a simple experiment, if we hit a stationary billiard ball with a cue ball, the two balls after collision will continue moving forward, and if we pay special attention to the motion, we will find that a specific point for the system moves in exactly the same way before the collision of the two balls and after the collision. This particular point, the motion of it will not change by whether collision occurred or it did not occur. That particular point is what we have called previously the center of mass. So, in such an experiment, the center of mass, as our experience tells us, the center of mass will continue moving in exactly the same way, whether the two balls hit each other or whether they miss each other. That particular point will keep moving. And that particular point, we can assign its position, we can locate it with time. We can assign a velocity for it, determine its velocity with time, and we can we can derive its acceleration. We can talk about it as if it were a particle having a mass equals the total mass of the system. So this point moves as if it were a single particle having the total mass of the system and located at the center of mass of that system. So this is general experience. The center of mass of a system moves like a particle. And suppose that we don't have only two particles. Suppose that we have, in general, an assembly of particles, n particles, 10, 15, 20, 100 million. And if we are concerned with the motion of the center of mass of that system, if we are not concerned with the individual motion of the individual particles, how they move relative to each other, if we are focusing our attention on the motion of the center of mass itself, then the motion of that point in space, which is the center of mass, is actually controlled and governed by Newton's second law, by this equation. The summation of F external is equal to capital M times A sub center of mass, Cm. What do we have here? We have a vector equation that has, in general, three components: the x component and the y component and the z component in our Cartesian coordinate system. F external is the external forces. The summation of F sub external is the summation of only the external forces acting on the system. Because we have to remember that every member of the system is acted upon by a number of forces. Some of these forces are coming from outside the system, which we call external forces, and some of these forces are due to the interaction of that particle with other parts of the system. Like if you have, for example, charges, a system consisting of charges, their charges repel each other or attract each other. Those are internal forces to the system. But we are not concerned with those internal forces in this formula, in this equation. This equation tells us that to the left-hand side of the equation, we have only the summation of the external forces acting on the system. And the mass M, capital M, is the mass of the total system. And A sub Cm is the acceleration of the center of mass of the system. So we have to remember those points, those key points, that we consider only the external forces. The mass is the total mass of the system. It's not a mass of one particle or two particles of it's the mass of the total system. And A center of mass is the acceleration of the center of mass. And thus, we realize that this equation does not give any information about the motion of the individual members of the system. This equation only tells us how to describe the motion of the center of mass, just one point in the system. And this one point, although it's a hypothetical point in space, just a point, as we said, it moves as if the whole system were concentrated in that point and having a mass equal to the mass of the total system. And that point moves accordingly in space. Now, we said that in this equation, we only consider the external forces acting on the system. But we know that we have forces of interaction between the various members of the system, the various particles of the system. Those are internal forces, as we said. Why are we not taking these internal forces into consideration in this equation? Where did these forces go? Because the motion of the center of mass is in general derived from the motion, from the summation of the motion of all the particles together. And when we consider the motion of any particle, we have to consider all the forces acting on this particle, whether these forces are external or internal, because relative to the particle itself, the interaction between it and the neighboring atom or the neighboring particle is an external relative to it. Relative to the particle itself, that force, which is internal to the system, but it is external to the particle itself. So if we are focusing our attention on the motion of the particle itself, everything is external, including what we call the internal forces of the system. So where did these internal forces go? Although they are in there, in the description of motion of the individual particles, why don't they appear in the equation that describes the motion of the system as a whole, of the center of mass of the system? That is a question that is simple to answer in terms of Newton's third law. According to Newton's third law, we know that the forces of interaction between two particles are equal in magnitude and opposite in direction. So when we add the forces acting on the whole system, we will have those internal forces, F acting on one, F1 acting on particle 2, and F2 acting on particle 1. Those are equal in magnitude and opposite in direction. So when we add them, they cancel to 0. F2 and 3 interact with two forces that are equal and opposite in sign or in direction, and they cancel. F3 and 1, also the forces between particle 3 and 1, also the forces are equal in magnitude and opposite in direction, and they cancel. And thus, all the internal forces which come from the interaction between a particle and another particle in the system, all of these internal forces cancel in pairs. They form pairs, an action-reaction pair for each one of them, and they cancel out when we add the total forces, and thus they do not appear in this formula. Now, how we have stated this equation, only the second law for a system of particles, but how can we derive this equation? Is it correct or not? It resembles the same shape of Newton's second law for a particle. But is it correct or not? We can derive that equation simply from the definition of the center of mass, the position of the center of mass. We know from previous discussion that the position of the center of mass, R sub center of mass, is equal to 1 over the total mass of the system times the summation of the mass of particle I times its position, and the summation goes from the first particle to the last particle in the system, assuming that the system has n particles in it, where the position vector is given in terms of its 3 components as usual. Now, if we derive this definition, this center of mass position, if we take the first derivative with respect to time, the rate of change of r center of mass, the first derivative would give dr center of mass by dt, which is simply v center of mass. And on the right-hand side of the equation, we will get 1 over m times the summation of mi times dri by dt. dri by dt is v sub I, which is the velocity of the particle number I. Now, if we derive this resultant, once again, we will get a derivative of the velocity, dv center of mass by dt, which is a center of mass. This is a center of mass equals, on the other side of the equation, 1 over m times mi dvi by dt, which is simply a sub I, the acceleration of the ith particle. And the summation is carried over the whole system. Now, if we multiply all the equation by capital M, which is the total mass of the system, we will have on the left-hand side m times a subcenter of mass, and on the right-hand side we will have summation mi times a sub I. Summation of mi a sub I is simply m1 a1 plus m1 m2 a2 plus m3 a3, etc., etc. And m1 a1 is simply f1 according to Newton's second law applied to the motion of a particle. m1 f1, where f1 is the summation of forces acting on particle number 1, and m2 a2 is equal to f2, which is the total external forces acting on particle number 2. That is using Newton's second law applied to the motion of the individual particles. So what do we have? Accordingly, we will have m a center of mass on the left will equal to the summation of the forces f1 plus f2 plus f3, which act on the particles number 1, 2, 3, and so on. And if we divide these forces acting on the individual particles into two categories, one is the external forces and one is the internal forces. So F1, for example, is equal to F1 external plus F1 internal, which means F1 external is the force, the external forces acting on particle number 1 that is coming from outside the system, while F1 sub-internal would be the internal forces acting on this particle as it interacts with the different parts of the system, with the remaining particles in the system. So if we divide the forces into F external plus F internal, we will have m a center of mass is equal to the summation of the internal forces plus the summation of the external forces. And as we mentioned, because the internal forces form pairs of action-reaction between each two particles, and the pair of forces are equal in magnitude and opposite in direction, so when we add summation of internal forces of all the system, that will give us 0, and we will end up with, on the right-hand side of the equation, with only the summation of F external. So we arrive at this result, which says m times a center of mass is equal to the summation of F external on the system of particles. And that is exactly Newton's second law for a system of particles. For example, if we consider a fireball, a cannon that fires a cannonball. The cannonball travels in the beginning on a parabolic trajectory, as we expect from the motion of the projectiles. Suppose at a given point in time on the trajectory, suppose that the ball explodes. Then the ball, which is considered to be spherical shape, and the center of it is simply evaluated to be the center of the ball itself, assuming that its density is uniform. Now, after exploding, consists of a system of fragments that result from the explosion. Now, according to the formula that we just mentioned a little while ago, Newton's second law applied to a system of particles, the fragments of the ball after explosion would travel exactly in the same way. The center of mass of these fragments will travel exactly in the same way as if the ball did not explode. So the center of the ball, if it did not explode, will follow the same trajectory as the center of mass of the fragments after explosion. And that will continue, the center of mass of the fragments will continue following the same parabolic trajectory as the ball would have followed if it did not explode, until the first fragment hit the earth. After the first fragment hits the earth, that's the last moment where we can talk about the trajectory of the center of mass of the fragments. After this moment, the first fragment hitting the earth or hitting a wall or hitting anything else, after that moment, we cannot talk about the trajectory. We cannot define it anymore, because we have one more external force, which is the reaction force of Earth acting on one part of the system, on any part of the system. This force, as the fragment hits the Earth applies a reaction force on that fragment, introducing a new external force that is applied now to the system that was not there when the ball before explosion was in flight. So we can talk with confidence about the trajectory of the ball and the center of mass of the fragments after explosion, until the first fragment hits the earth or a rock or a wall or whatever. And then after that, we cannot determine the trajectory anymore. And that is an illustration that the center of mass of the system of particles would travel or would obey exactly the motion of the center of mass, whether the system has scattered or if it didn't scatter. If we concentrate the total mass of the system in the center of mass, or if we keep it scattered, it doesn't matter. It will move in exactly the same way. That's according to Newton's second law for a system of particles. That's what the equation tells us. And now, at this point, we are ready to define another quantity of importance in physics, which is linear momentum. Linear momentum for a single particle, we call it P, and it's a vector quantity, small p. This quantity, linear momentum, is defined as the mass of the particle times its vector velocity, times its velocity vector. It's a vector quantity, and because it is the velocity vector multiplied by the mass, then we conclude that the direction of the momentum is in the same direction of the velocity of the particle. In fact, when Newton wrote his second law of motion, he did not write it in the form that we have shown. Summation of F is equal to ma. He actually wrote it in terms of the rate of change of momentum. And this law states that for a given particle, the summation of all forces acting on the particle, if the particle has dimensions 0, if it's a point-like, then all the forces acting on it are, of course, external. Anything is external to it. So the summation of the forces acting on the particle is equal to the rate of change of its linear momentum. That is the general form of Newton's second law, and that is how it was originally stated. Now, what is the connection between this form and the form that we have discussed previously? The form that we have discussed previously is a special case, is a special form of this law, where we can, for example, use the definition of the momentum, which is m times v. If we derive this quantity, dp by dt equals m dv by dt, and dv by dt is simply a, that will give the forces acting on the object is equal to m times a, because it's coming from m times dv by dt. The mass is a constant, and the derivative of it is 0 simply. The next step is to evaluate the linear momentum of a system of particles. Having defined the linear momentum for a single particle, we have the facility now to define the linear momentum of a system of particles consisting of n particles, for example. And because the linear momentum is a vector, then as we know from the properties of vectors, the total linear momentum for the system, capital P, is simply equals to P1 plus P2 plus P3 and so on until we reach the last particle. And this is simply equals to m1 v1, that's substituting for the P1, for the momentum of the particle number 1, plus m2 v2 plus m3 v3 until we reach mn v sub n. And from the definition of the center of mass position, if we derive r sub center of mass, we realize that this quantity m1 v1 plus m2 v2 plus m3 v3 until mn vn is simply the total mass of the system times the velocity of its center of mass. So we arrive at this conclusion that the linear momentum of a system of particles is equal to the total mass of the system times the velocity of its center of mass. And at this point, I would like to end this lecture and thank you for your attention.